Alright, in this second example video, we actually have two examples. One is going to go quicker than the other, but let's get started. So W bounded by these constraints, set up a triple integral to find the volume of W. Now, maybe some of you can see this thing and can do this without a picture. If you need a picture or want a picture, I encourage you to do it before actually beginning this problem. So here we go. So if we think about this, this is going to be a plane. This first one is going to be the region under a plane in the XZ direction, and Y is going to be free. We know that Z is positive, and we're also restricted to the unit circle. So in terms of the XY space, okay, so here's 1, and then we're going to have something like this go on. And so that's our bottom of our region, okay, and then we have something like this going on too. And so let's see if I can draw it accurately. So we're on a plane and we're restricted to the circle here. And so we have a height here, something like that, and it looks something like that. Okay, yeah, that's actually not too bad. So it's kind of like a cylinder that we've cut at an angle and rounded the edges. Okay, so if we set up a triple integral, okay, again, you can do any order that you so choose, and you could even do different coordinates if you'd like. The order of integration that I'm going to do here is just going to be, I'm going to use Cartesian, and I'm just going to use dx, dy, and then dz, dy, dx. Okay? So in terms of x, x is going to go from -1 to 1, because it's on the unit circle. Okay? And then similarly, when we do y, y is again restricted to the unit circle, but in terms of x, it's going to be -1 by, or 1 square root x, or negative square root of 1 minus x squared to positive square root of 1 minus x squared. And then for z, if we think about z should extend from 0 up to this plane boundary, so 1 minus x. Okay, so this one wasn't too bad to set up. Again, just thinking about your elementary regions and setting those up in terms of the other variables. All right, so that was kind of what we did in the last video as well. The last example that we're going to do is one where we can't actually draw it. So find the volume of the solid in the first octant. Okay, so bounded by the three planes, x equals 0, y equals 0, z equals 0, and so we're in that first octant, and then we're also bounded by this curve, x cubed plus y cubed plus z cubed is equal to 1. Okay, so now you're probably thinking, well, what do we do here? And, well, the thing is, it's not going to be pretty to evaluate using standard Cartesian, so I'm going to do a change in coordinates. It would be really nice if this was like u plus v plus w, or u plus v plus, yep, we use u plus v plus w is equal to 1, because that's a nice plane. So why don't we just define x as, or x to the 1/3 is u, y to the 1/3 is v, and z to the 1/3 is w. So if I rearrange that, or look at it a little bit differently, am I not saying that x is u cubed, y is v cubed, and z is w cubed? Okay. Okay, yeah, I mean, that's true. And so then we just get u plus v plus w is equal to 1. Okay, and if I use the change of coordinates, I need to find the Jacobian associated to it. Okay, so let's find the Jacobian. So we have partial of x, y, z with respect to u, v, w. Okay, so this is going to be, okay, now I go through and differentiate everything with respect to u. Okay, I get 3u squared, 0, 0, 0 and 0. Oh, that's not too bad. And then with respect to v, 0, 3v squared, 0, and then with respect to w, 0, 0, and 3w squared. Alright, that's fine. And so I do this, the determinant, and since it's diagonal, it's really nice. I just get 27 u squared v squared w squared. Okay, so that's my Cartesian expansion, or my Jacobian, and then my expansion factor. Okay, so then if I go and look at the region of integration, and I'm finding the volume, right? Okay, so, and I should actually say I can sketch it, I just choose not to. But we are 1 times the Jacobian, so 27 u squared v squared w squared. Okay, and then I pick an order of integration. Oh, I don't know, let's do dw, dv, du, just for fun. U is going to go from 0 to 1 at most. Okay, and then I have to use this to find the bounds of the other functions in terms of the other variables. So v needs to be in terms of u, and if I do that, I believe it should be 0 to 1 minus u, and then lastly for w, 0 to 1 minus u minus v. And that, my friends, is going to be the integral, which you can evaluate and evaluate to find the volume. I'm not going to go through the volume though. All right, so a different example, not using our standard Jacobians. So remember always to include that. And that's going to conclude the videos for this week.